we'll introduce the speaker in a moment, but let me just say that, I've been coming here for 26 years, and actually that's the first time I met the speaker. He and I were young postdocs at the time. And the kind of work that goes on here during these summer and winter sessions are, people come together and have these discussions, and a lot of ideas bubble through the activities that happen during the week in the winter and the long summer workshops. This week, we have a program on quantum matter, the era of quantum computing. And this is an area, as you know, you have been following quantum computing in the news probably. This is an area in which the physicists here this week are exploring different kind of materials that could be very useful to create quantum technology. So, and this is where our speaker, Amir Yacoby, comes from. Amir Yacoby, a professor at Harvard, is one of the pioneers of developing kind of experimental techniques to sense quantum phenomena in materials. And he got his start actually as an aeronautics engineer. And he wasn't going to be a physicist at all. But then he switched in his graduate school and became an experimental physicist at Weizmann Institute. He got his PhD. And he was at Bell Labs in New Jersey, working with Horst Stormer, who won the Nobel Prize. And after which he went back to Weizmann rose through the rank. And in 2006, he moved to Harvard University. We did try to get him at Princeton, but we failed. And he's been, as I mentioned, developing advanced measurement technologies for exploring quantum phenomena. He's won many prizes and awards. He's a member of the American Association of Advancements of Science. He's a member of American Academy of Arts and Sciences and a member of U.S. National Academy. And he's been a good friend for a long time. We've spent a lot of time here in Aspen together. And I think it's useful to always sort of embarrass the speaker a little bit to loosen the crowd. So, he's going to tell you about quantum sensing. So I want to show you a little video where he explores sensing in a different sense of the word. He took me on a camping trip last summer where we came to Aspen together. And four-pass loop, I'm sure many of you know loop. So he almost killed me on this trip. And I won't show you all the instances. So this was the start of the trip. I'm not much of I'm a fit guy, but I'm not much of a camper. And this is the start of a trip. And he's doing some sensing. If you see, we came across this barrier, and and I was like, okay, how are we gonna get across that thing? We're gonna know sure if this could have ended very badly, as you can see. You see, I have a lot of respect for the speaker, and here I am basically gingerly following him through. So I'm really looking forward to his talk. Please welcome Amir Yacoby.
Well, thank you, Ali, for this very embarrassing introduction. Kind, but embarrassing. What Ali did not tell you is that I started actually as a theorist when I switched from aeronautical engineering to physics. And I was always envious of my experimental colleagues that had these amazing laboratories and very expensive toys to play with. Eventually, I dodged the bullet and decided to switch to experimental physics. And I'm really excited to be able to tell you a little bit about the expensive toys and games and tools that we've been developing over the course of the past several years to gain some new insights into quantum material. So our understanding of nature has begun a long, long time ago when we didn't really have many tools, and we were only able to explore nature directly through our senses. And so it's allowed us to look at light scattering, for example, through raindrops, understand rainbows, explore the motion of planets and stars, look at the tides and connect it with the motion of the moon, listen to thunder, etc. But as you all know, today, our understanding of nature reaches far, far beyond what our senses can see directly. And for example, we know that the universe began more than 13 billion years ago, and that it took several 100 million years after that for the universe to cool down and to matter to start forming stars and galaxies. And on a more earthly scale, we can see that there is matter on Earth, but we know that matter is composed of atoms. These are already things that we cannot see with the bare eye, and that these atoms themselves are made of electrons encircling a nucleus. The nucleus is made of even smaller particles, protons and neutrons. Those are made of more elementary particles, quarks. So how is it that we know so much about our universe where we can't even directly see it? And the way we understand this is the secret is basically our ability to devise instrumentation. It allows us to connect really interesting physical phenomena and effects that happened billions of years ago and are on extremely small length scales with our senses. When I transitioned from theory to experiment, one of the things that I realized was that all the instruments, or nearly all the instruments that I had in my lab, did not report quantity that they're measuring. So what I'd like to talk about today in depth is, what do instruments really measure? This would be kind of the theme of today's presentation. So to start off, I'm going to start with an instrument that you're all familiar with and you're using daily, multiple times a day. And that's GPS, Global Positioning System. And we all know that a GPS is a measurement apparatus, and it tells us our position with very high accuracy. I want to ask, what does it measure? This is a question to you. Any ideas what this instrument is actually measuring?
It's the arrival of radio signals at very precise times.
That's right. It is measuring time. And the way it does it is we have this set of orbiting satellites that surround Earth, and they're transmitting signals constantly towards Earth. And there's a timestamp on these signals that contains the time in which these signals departed from the satellite. What this instrument has is basically just a timer. It is measuring how long it took these signals to reach the satellite to the instrument. And because the satellites are distributed surrounding Earth, there are different times that it takes the signals to come from different satellites. And one could then imagine that one can connect the time to our position. In fact, this task of connecting the time to our position is extremely complex. And if you really want to get the accuracy the GPS units have today, you really need to use Einstein's general theory of relativity. It takes into account the deforming of space-time because of the gravitational field of Earth and the Moon in order to account precisely for connection between time and position. So the theme of today's talk is basically to really appreciate the fact that when we have a piece of physics that we understand and understand well, we can connect between quantities that we know how to measure and quantities that we're interested in knowing something about. And a lot of the advances have come due to basically inventing new connections, taking advantage of new chapters of physics between quantities that we know how to measure. And sometimes these quantities are quite boring. Measuring time doesn't seem like a very difficult task. And reporting a quantity that is much more complex and interesting. Now, once we are able to measure something, we can basically lump it into, there's a cascade. So we can basically say, hey, now we know how to measure position, or GPS measures position. We can ask, okay, so what other physics can we use in order to report something additional? So for example, if you hold your GPS in your car and you're driving, and you know what your velocity is, then you can use kinematics to report your estimated time of arrival. Could be a cascade of these connections between what we know how to measure, what we're interested in reporting. So over the course of many years, my group has been really straddling the boundary between developing new probes to look at quantum matter and using those probes to get new insights into materials. And of course, both discoveries made across the community and our own discoveries can then lead back again to developing new probes, and the cycle continues. What I'm showing here is just a few examples of new measurement capabilities that we've been developing. I'm not going to talk about all of them. I'm going to talk today about these two probes that allow us not only to gain new insight into materials, but they also allow us to visualize them in real space. So they have spatial resolution. And I'll talk much more about these probes throughout the talk. Now, before I dive in how these probes work, what do they actually measure, and what do they report, I want to motivate a little bit, why is it that we actually need more probes? Already we have a fantastic set of probes which have brought us to our understanding of our universe today. Why do we need more? And part of the reason has to do with the complexity of the materials we're interested in. And I'd like to give you a little bit of a flavor of what that complexity is. So we know that an electron, we mentioned it already, it's surrounding, kind of running in circles around the nucleus in an atom, and it's a fundamental particle of nature. So in the fundamental theory of elementary particles, this particle cannot break apart anymore. It's the basic unit. It carries a charge E that has a spin that you can think of as encircling of the charge around some axis, and in units of Planck's constant, its angular momentum is 1/2. And it's a very simple particle. There's really no surprises. We know a lot about the electron when it's in vacuum. But what's interesting is that when you look inside a material, there are actually huge, vast numbers of electrons, and they're actually very, very close to one another. They're strongly interacting with one another. What this leads is to emergent phenomena that take place inside of the material. And the best way to understand these emergent phenomena, it turns out, is in terms of new emergent particles. When one discusses the material in terms of those new particles, the description becomes simple. Whereas if we had to describe what's going on in the material in terms of these interactions between electrons, it becomes very, very complex. I'd like to give you a few examples here, a handful. There are many, many more of what kind of emergent particles can appear inside solids. So here is an example of a particle called a skyrmion. It contains the same charge as one electron, but its angular momentum consists of this very complex texture spins. So instead of having a spin of 1/2, it could have a spin which is much, much larger than 1/2, and it has this peculiar texture spread out in space. Another example is, you probably know that electrons, once they're subject to magnetic fields, they start moving in circles. Magnetic field pulls them like it's a central force. It basically makes the electrons move in circles. Then some materials, we have emergent particles that we call composite fermions, such that when you subject them to very strong magnetic field, they actually start moving in straight lines. When you remove the magnetic field, they are actually moving in circles. It all has to do with the interactions of the electrons among themselves. Under other conditions inside the material, you can have a situation where this elementary particle is no longer elementary. And in fact, the electron fractionalizes. It breaks up into smaller constituents, each of which has a fraction of the charge. For example, here, it's fractionalized into a charge E/3. Lastly, these examples are charged particles, can have also neutral particles. And here you see an array of electrons sitting inside a material. The charge can no longer move. It's kind of crystallized. The spins interact one with the other to form these spin waves. And the interesting thing about these particles is that they contain no charge. They contain a spin identical to that of a single electron, spin 1/2. A lot of peculiar particles. The question is really, how can we probe, how can we test these hypotheses? These are kind of theorists' imagination of what is going on. Do these particles have real existence inside the material, or it's just our figment imagination? So Our task is really to devise new measurement apparatus that can allow us perhaps to observe, visualize these particles. And then we can also ask, what can we do with them? So in this talk today, I'm going to give two examples of probes that we've been developing and perfecting for many years now. The first one relies on very peculiar defects that live inside diamond. And you'll see that these defects allow us to measure magnetic fields very precisely. And through that, we can visualize these neutral spin wave excitations. And the second probe that I like to describe is one that relies on the granularity of charge, the fact that the charge of an electron is finite, it's not small as we want it to be. And based on that, we'll see that we can visualize the fractionalization of charge. All right. So let's start with the first probe. So the probe is made of diamond, and one of the nice things about diamond is that it could be extremely pure. But we're actually not interested in pure diamond. We'd like to have some defects in the diamond. What you can see here is a specific defect consisting of a missing carbon atom. So one carbon atom was removed from the diamond lattice. Another carbon atom was replaced with the nitrogen. The nitrogen has one extra electron. This defect is atomic in size, and it has an axis that connects the vacancy and the nitrogen. And it turns out that this defect allows us to measure magnetic fields along this axis. So why is this special? So if you shine light on this diamond and it has this vacancy, this nitrogen vacancy center, this defect, it turns out that it's going to emit light in the red. So diamonds that have a lot of these defects, if you look at them, they're going to look reddish. So if you ever have a diamond that's reddish, you know it has these kind of defects. In fact, there are different kinds of defects in diamonds, some that would look yellow and other colors. Basically, they're all reflecting the properties of the defects that exist inside the diamond. A diamond is a very, very good insulator, which means that it has a really large energy gap in which electrons cannot reside. But the defect actually allows us to position electrons inside the gap. And this is very important because the fact that this defect is so remote from where the electrons can reside means that it's very isolated and can therefore be very, very clean sensor of magnetic fields, as we'll see. Now, this center is not very complex. It has only 3 energy levels. And the way these energy levels depend on magnetic field is shown here. The ground state is completely invariant to magnetic field. It doesn't care at all about the external field. The 2 excited states evolve in magnetic field linearly in a way that we understand very, very well. So the relationship between the energy of this state, or the frequency, and the magnetic field is set by constants that we know very precisely. This is basically the key, because what we're going to be measuring is this frequency, and we're going to then know what the magnetic field is. So how does this work? So one interesting thing about this defect is that in the process of shining light on it, we can initialize this defect in its ground state. This is very peculiar because the energy difference here is quite small. And this diamond can be sitting at room temperature where energy associated with the fluctuations due to temperature are much, much larger. And yet this pumping process where we shine light can prepare it, it cools it down temperatures that are far, far below the temperatures we're at. Very, very cold. Second thing that's very interesting about this defect is that we can know simply by the intensity of the emitted light, we can know whether it's in its ground state or in one of the excited states. When it's in its ground state, it emits a lot of light. And when it's in its excited state, it is quite dim. So this is a very cool feature of this defect that we're going to be using. So now the question is, how can we determine magnetic field in this system? So what we're going to do is we're going to shine microwaves, which have an energy which is comparable to the energy separation between the ground state and its excited state. We're going to tune the frequency. And what we're going to be looking for is to see at what point does the light get dimmer. Because once we found the right frequency, that matches the magnetic field, we're going to be able to excite our defect from the ground state to excited state, and we're going to see reduction in the fluorescence. And this then tells us precisely what the magnetic field is. So this is the principle of operation. It's actually not that complex. We basically can determine the magnetic field by identifying what frequency excites this defect. Now, it has two additional features. One is that it can operate at broad range of temperatures, so it's very convenient. We're not restricted in temperature all the way from very cold to very hot. And it has nanometer resolution because the defect itself, its size is atomic. So if we can bring it close to whatever we're interested in, we can image things on an atomic or near atomic scale. So the next thing that we've done is to take this defect, and the physics of this defect has been studied for many decades now. But only about a decade ago, we started using this defect as a sensor. So what we've done is we've fabricated these platforms of diamonds. So this is all a monolithic piece of diamond that has one little pillar at the end. And at the end, we have one of these defects sitting just very close to the tip. We put this on a microscope that we can move this tip around and scan this defect, enables us to image magnetic fields in real space. Very high precision and very high sensitivity. So in the spirit of our talk today, we know is how to measure the intensity of the emitted light. We understand the physics of this defect very, very well. That allows us to report magnetic fields with spatial resolution. In fact, this defect, I didn't explain how, but it allows us also to measure temperature and electric fields with less precision, but nonetheless, it's sensitive to these quantities as well. And it's all because we understand this piece here in the middle. Now, once we know using this physics to report magnetic fields, we can take it one step further and use additional known physics to report even more interesting quantities in quantum materials. And this is what I'm showing here. Over the years, we've explored each one of these arrows is a different chapter in physics, which allows us to connect magnetic field with some interesting physical property inside a material. So for example, we're able, just by measuring magnetic field with this defect, to realize a three-dimensional magnetic resonance imaging setup, very much like you have in a hospital, only that we can image the spins inside the material with a resolution of about a nanometer. Can't do it on a body scale, on a human scale, but on a small piece of material, we can see where the spins are with far, far better resolution than you have an MRI system. Typically, spatial resolutions there are on the scale of a millimeter. So 6 orders of magnitude better using this kind of physics that connects magnetic fields to the fluctuations of free spins. Talked about skyrmions and this spin texture. We're able to image this texture of magnetization. We can explore interesting properties in superconductors. We can look at the way current is flowing inside materials through the connection of current and how it's generating magnetic fields in real space. And we can image these neutral excitations that I mentioned to you earlier, these spin waves that carry a spin on half. I'm going to elaborate a little bit more about this. So how is it that we can see these spin waves? So we need to recall that the electron that has this spin is like a magnetic moment. And this means that it's generating a magnetic field lines, very much like the Earth's field lines. It's on a very small scale, but nonetheless, as these spin waves are propagating, what happens is that the magnetic fields they're generating are oscillating, and we can pick this up with our tiny, tiny sensor here. What you see in this movie are exactly wavefronts of these spin waves propagating in space. The spatial extent is a few microns, and we can image those very, very beautifully in time and in space. So the question I'd like to address now is, well, great. So now we know how to measure spin waves. Can we use this for something? Is it useful? Can we devise another measurement apparatus based on our understanding of spin waves? For this, I'm going to digress just a little bit and tell you about scattering experiments. You've all played and done scattering experiments. You take a flashlight and you shine on a particular, on a sample, and you look at the screen. And the challenge in a scattering experiment is to look at the scattered light on the detector on the screen and to be able to infer was the target. This is the name of the game. And in physics, this is a little bit more precise. What we are using are waves or particles. These could be X-rays or electrons. I'll talk a little bit about them. They have well-defined energy and momentum. They're very coherent. They're propagating in vacuum. They then impinge on a target and diffract. And if we're able to measure far away, where there's no material anymore, if we're able to measure the amplitude and the phase of the scattered waves, we can then reconstruct some property of the underlying material. The cool thing about this thing is that we don't need to measure in the area where the interaction is complex. We can measure far away, places where these waves are non-interacting, we understand them very, very well, and yet we can then say something, we can trace back, we can reconstruct what the target was. So physicists love scattering platforms, and there are quite a few, and I'm showing them here. The light scattering, for example, that I mentioned earlier, this is just one example, of course, is being used today by observatories in order to correct for aberrations that the atmosphere produces. So if you have a star that you want to image far, far away, when the light from that star comes to the observatory, it passes through the atmosphere and it gets distorted. So the images look really blurry and bad. What is done then is to use a very powerful laser, shine it up through the atmosphere, and from the reflected light from this laser, one could measure what the aberrations are of the atmosphere, and then using adaptive optics, correct back to eliminate those aberrations. And one can then obtain really sharp images of these stars, despite the fact that the atmosphere is scattering the light. One can replace the source with neutrons. Neutrons carry spin, and this allows us to learn something about particularly magnetic materials, about their internal structure, some of their excitations. One can replace the source here with electrons, and this is what's known as electron microscopes, transmission electron microscopes, and these allow us to see even things down to the atomic resolution. And there have been tremendous developments in this area over the past several years. Of course, X-ray scattering you're familiar with from the hospital, where you can see your bones. But under different conditions, X-rays can really teach us very detailed information about matter and its structure. So what we were curious is to see, well, can we devise a scattering experiment, spin waves? Now, the difference here, of course, is that unlike X-rays or neutrons that can propagate in free space, these particles exist only inside matter. If I were to try to pull these particles out of the matter, I would have to construct real electrons again. So these peculiar creatures only live inside the matter. So this means that we need to think a little bit differently, and we need to invent a different vacuum. So what we're advising is, you see this kind of gray slab. This is a thin layer of magnetic material that can support spin waves. These are, in fact, the spin waves that I showed before. And this would be our vacuum. Turns out that in this material, it's called yttrium iron garnet, spin waves can live and propagate very long distances without any scattering or any interference and without any decay. So they're very, very coherent. We know how to launch these spin waves using just an electrical wire here that can send some current through, and the magnetic field generated by this current can launch spin waves. Their wavefronts are just going to be parallel to this electrode. So this is where this image came from. These are exactly these spin waves imaged on their way to a target. You can see that we can see the wavefronts very, very precisely, and we can extract both amplitude and phase. Now the interesting things comes when we try to image what happens after the target. So how does the image look after the target? And as I explained, we can do both an amplitude and a phase map. And this is the amplitude map. So each color here represents the amplitude of the spin wave. It's a wave. And you see that where the target is, which is this white circle, the interaction is very, very complex. And we don't want to bother ourselves with that because what we want to look at is far away from where the target is. We're going to be analyzing the response, the scattered spin waves, far away from the target, both the amplitude, and this is the phase map. Again, very complex. Near the target becomes much more simple far away. And using these two pieces of information, we'd like to reconstruct the properties of the target that scattered our spin waves. Yeah.
What material?
Is the target? The target is another magnet. It's a hard magnet. Thank you. The question was, what is the material that the target is made of? So if we try to reconstruct, we have an expectation. So the target, as I just said, is a magnet, and it has all its magnetic moments in the plane pointing in some direction. And I'm not going to go through the details, but it turns out that what the scattering is doing is looking at the derivative, the change of this magnetization in space. You see that if this disk is kind of a sharply defined, the magnetization is constant, so it's not changing in the middle, it's only going to change at the boundaries. And since this is only the change in one coordinate, it's only going to produce a signal on the top and on the bottom. And they have opposite signs. So this is what we expect. We expect a positive target signal at the top and a negative one at the bottom. And in fact, what we find is something quite different. We see that the entire sample is participating in scattering the waves. This is something that we don't really understand yet. It's not behaving as a very rigid magnet, even though that's what we thought it should do. And I think it's a very nice example of a situation where you have a new measurement capability and it reveals things that you did not expect because you have a new way of looking at the material properties. So again, in the spirit of this talk, for now, we know how to measure magnetic fields. Using the physics of spin waves that we understand very well in our vacuum, we can generate a target that is scattering these spin waves, and we learn something new about our material. So before moving on to the second probe that I wanted to describe, I wanted to ask if there are any questions on the first probe, what it can do. Yeah.
What is the size of the tip of the diamond with respect to the size, if you like, of an electron? Because in that, I mean, that looks tiny. That can't be the correct scale, right?
That's right. Yes. So this is obviously an animation. So the size of the tip is about 100 nanometers. So it's very, very big on an atomic scale. But the size of the defect that sits at the end of, so the question is, what was the size of the tip and how is it in relation to the size of an electron? So the size of the tip is about 100 nanometers and the size of the defect that sits at the end is atomic. So the fact that the diamond is big is not important at all. Really what's important is the size of the defect because that's the sensor.
Yeah.
Sensor is sitting inside a matrix. I don't care about the matrix. It's really the sensor itself. Okay. Yeah.
Requisition a flawed diamond to build this thing. I mean, where do you find one of those?
You go to the jeweler and you take a piece of ring and you cut it. No, so these are artificial diamonds, and for some reason, these artificial diamonds are not regarded in the, in society as something very valuable because what people like are diamonds that you pick out from the center of the earth. So these are artificially grown. There are two ways of growing diamond artificially. One in huge reactors that produce pressure and temperature very similar to what you find in the center of the earth. And the other is what's called CVD. It's a process where you grow them layer by layer. So these diamonds were grown layer by layer. But they're very, very high quality. In fact, one can grow them with very, very few defects, much less defects than the real jeweler's diamond. And yet they cost much less. All right. So the second probe I'd like to talk about is this one, which measures potential. This one measured magnetic field. This one is going to measure potentials or electric field. And it really relies on the granularity of charge. So to get a sense of why the granularity of charge is important, let's do kind of a thought experiment. We have a bucket and it sits on a scale, and we're going to pour sand, and we're going to look at how the weight of this bucket is changing over time. And of course, it's rising, but because the sand is granular, if we were to look very, very carefully at this curve, we would see that the mass is actually increasing discretely. Each time one particle of sand lands into the bucket, mass increases, and then nothing happens until the next one, etc. So this is the manifestation of the granularity of material. Question is there an analog to the granularity of charge? We're looking for something that would look like that. We're going to pour some electrons into a bucket, and we're going to have a charge sensor here. We want to see how does the charge increase inside this bucket. And this kind of apparatus is actually a device that you're probably familiar with. It's called a capacitor. Capacitor is a bucket of charge. And schematically, what it consists of is two metal plates. Here I have one big one and a small one. And when you apply a voltage between these two metal plates, what the battery is doing is it's forcing charge from one electrode to the other. And there is a very simple relation between the charge, let's say on the small plate, and the voltage that we apply between the plates. It's a linear relation. The coefficient here, C, known as the capacitance, depends only on geometric quantities. The area of the disk, and the distance between the disk and the bottom plate. So now electrons have a finite charge. So if we were to zoom in on this curve, we would expect to see something that looks like that. That the number of electrons is changing discretely. We're going to change the voltage, and in a certain range of voltage, nothing is going to happen. Then at some point, one more electron is going to hop on. Then again, nothing will happen, and so on. So another way to understand why system requires this kind of discreteness is to look actually at the energy stored in this capacitor, the fixed voltage, as we vary the charge. So this is the energy, and this is the charge. We're keeping the voltage constant. And what we're seeing is that the system really doesn't want to have any other charge than the one given by that relationship. So if we were to change the charge, we're going to sprinkle more electrons onto this disk here, the energy is going to go up. So if the system wants to be in its minimum energy, it's going to end up having the charge that's given by this simple relation, capacitance times the voltage. Now, the problem here is that charge is no longer a continuous variable because the electrons are discrete. They have a finite charge. So we can't look at this curve continuously. We have to look at it at values that are integer multiple of the charge of the electron. So here is a situation where the minimum energy of this capacitor is given by some number n, but it's an integer, times the unit of charge of an electron. And the system is very happy. It's going to have n electrons in it, and we wouldn't want to have neither n minus 1 nor n plus 1. But now we're going to change the voltage just a little bit. So what we're doing is we're trying to increase the charge on this plate. And what's happening is that, yes, the energy of the n plus 1 electron state is coming down, but the n electron is still the ground state, still lower energy. It's just these dots are moving on this parabola. We can do it further, and still the ground state is n electrons. So the charge is not changing, not changing, not changing, till we reach a very peculiar situation. The energy of n electrons and n plus 1 are equal. If we now push the voltage just a little bit more, one electron will hop onto the plate. The system will have n plus 1 electrons. So there are two generic configurations to this situation where we have discrete charge. One that I showed here, lowest energy configuration is given by n electrons. And the second is shown here where the lowest energy configuration is ambiguous. It can either be n or n plus 1 electrons. They have the same energy. This has tremendous implications we can detect if we connect electrodes to this small plate here. So what we're envisioning is let's connect two electrodes so that we can send some current across. And these electrodes are only coupled very, very weakly to this plate here, because if it was coupled strongly, then electrons could easily leak out. So we want it to be coupled very, very weakly so that the number of electrons on this plate has to still be an integer. Now we're going to try to send current from one electrode through the plate to the other. And in the process of sending current, obviously I need to take an electron from this plate. I need to move it onto this one and then take it off. So the charge here has to go from n plus 1, back to n, etc. And we see that these two configurations will give very different results for this process, because under these conditions, we don't have enough energy to go from n to n plus 1 back to n. So current will not flow. Whereas in this condition, there is no penalty to go from n to n plus 1, and current will flow. So this is how the current as a function of the voltage looks like. In the bottoms here, we're in this configuration where current is blocked. Cannot send any current across the device. And then when we reach close to this condition, suddenly current turns on, and then it's going to turn off when we have n plus 1 electrons. So what's remarkable about this curve is that if you were to measure this current, you can just count the electrons one by one as they're entering onto the plate. This is an electrometer with fantastic sensitivity. In fact, if you position your device right here, you can turn this electrometer, which just counts electrons, to a potentiometer. Current here is extremely sensitive to any changes in voltage. And that's why this device measures voltage very, very precisely. And it does it also on a very small length scale, because this disk here has to be very small. And I'd like to explain that because this is going to be very important for the next example of what we do with this sensor. So we can ask, what is this change in voltage that is needed to change the charge state by 1 electron? So we just plug in this formula. We use this formula. We see that the change in the voltage is just given by 1 electron divided by the capacitance. And we plug in this capacitance. And the important thing to take away here is just that this voltage scales as 1 over the area of the plate. As we make the plate bigger, its voltage that's needed becomes smaller and smaller. So as we make this disk bigger, the separation between these peaks becomes smaller and smaller. If the disk becomes too big, all these oscillations are going to merge, and we're not going to see any change. So that's why it's very important to be in the limit where the disk is small. And that's also to our advantage because we want to measure potential with a high spatial resolution. I didn't mention what these widths of these peaks are. They're directly a measure of the temperature of the system. So that's why this sensor is also a very good thermometer. So again, what we have done is we are measuring current, and we're using the physics known as Coulomb blockade. This physics was discovered towards the end of the last century by these 3 gentlemen, Ted Fulton, Jerry Dolan, and Mark Kastner. They found it by surprise. They were basically playing with current flowing through very narrow channels, and they suddenly saw this kind of physics, and it took quite a while to realize what is going on. Now we understand that basically is the physics of what's called Coulomb blockade. It's this discreteness of charge that allows us to turn on and off current very sensitively, depending on the potential in the vicinity of this device. So now that we know how to measure potential, we can ask, okay, can we use further known physics to explore various physics phenomena in quantum materials? I'll talk about the measurement of fractional charge, but I just want to mention that we can use this device through understanding, again, of another chapter in physics. We can see what's called phase transitions. We can image skyrmions. These are these charged particles that have the peculiar spin texture, and we can learn something about the topology of the material that I'm not going to talk about at all. So under what conditions can charge fractionalize? So I'm going to step back and take a look at a material which allows electrons to move only in the plane, and they're moving in straight lines. It's a very clean piece of material. They're just zooming across various velocities. When we subject this material to very strong magnetic fields, turns out that electrons start circling. You see that what has happened primarily is that all the electrons localize. Whereas here they could really explore all the sample. Here they're all just moving around some center. They're no longer moving. They're just kind of stuck in space. Now, if the sample is not that clean, it has some potential landscape, some topography. And what happens is that these electrons are moving along constant potential contours. They're maintaining their altitude on this topography. If the magnetic field is super large, you're just going to be encircling the peaks or the valleys, this potential landscape. But the main point is that electrons localize in space. This is going to be important. Their localization is what's going to allow us to see them. So we're going to take our sensor and we're going to put it above this layer of material. And we have our bottom plate. So this is our capacitor that I described before. We have a plate here that we can change the number of electrons in this plate as we vary the backgate. Now, if this top electrode here is very, very big, remember, when the area is big, the voltage is needed in order to change the charge state here by one electron is tiny, tiny, tiny. And we're not going to see any discreteness because all these oscillations, these peaks are all going to be merged together. But under the conditions where the charge is localized, suddenly the area in which the electrons move into in this plane is very small. And so we're going to see discreteness that appears in this measurement. And if we take the derivative of the potential that we're seeing with respect to this voltage, we're going to see these sharp negative spikes. So we can imagine how a measurement would look like. Suppose we're moving our tip along a line here. So we have electrons localized at different locations, and if we can pile a few of them at each location. So what we're going to see are these streaks of negative signals as a function of position and as we're changing density. And the reason these are not just horizontal lines, they're curved, simply because we can have a little bit of charge on the tip that would then change the condition under which we want to charge each one of these states as we move the tip. So you can ignore the curviness and only consider the bottom. That's the condition under which the charge actually enters into these states. All right, so here is another heuristic artistic rendering of the potential that exists in our material. And we're going to be scanning along this line. And this is the measurement that we find. So you see these very sharp negative curves. This is not an artist rendering. This is a real measurement. This is position in microns, and this is the change in density. The way we can understand this picture is by moving density as we're filling. Once we hit this bottom, one electron hops into this location. And then as we're raising the density some more, suddenly an electron hops into this location. This process continues discretely, one electron at a time, until we filled up these states and we start filling up more of these valleys inside this picture. So this is a direct imaging or visualization of electrons localized in this material. Now, the thing that we're after is fractionalization. So imagine that the unit of charge changes from being 1 electron to E/3. Nothing else changes. So the potential landscape is the same. Everything is the same. Just magically, you reduce the unit of charge by a factor of 3. So we immediately see that we're going to have 3 times more charging events because we can now charge these pockets 3 times three times the number of events because we're filling 1/3, 2/3, 1, 1/3, 2/3, etc. So we're just filling up this. So we're going to see many, many more lines. In fact, the number of lines we're going to see is just going to be 3 times the number of lines we saw before. This is really what you see. So if we change the conditions of this sample, and it only involves changing magnetic field, the system indeed behaves as if it fractionalizes, and here's a real measurement. Now you see that in the same locations where charge was filled before, we have 3 times the number of lines, and the physics is really adding these fractionalized particles into the same pockets in space. So this is real space visualization of these fractionalized particles. And of course, these particles exist only inside the matter. If you want to grab one of these 1/3 and pull it out, what's going to happen? It's going to grab another 2 of them, and they're going to form 1 electron. So you cannot do it. This technique allows you to see them, but they're really, really there. So again, we've done is we're measuring the current through this device and through the understanding of the granularity of charge and how it affects the charging properties of the device. We can connect it and we can visualize in real space fractionalization of charge. I'm coming to the end of my talk, and I really want to hammer this message before closing. That is that there's a lot of fun in discovering new physics, but really one thing that we should do more often is ask, well, once we understand something, and I challenge you to do it for things that you understand, you can ask yourself, well, what can we measure? What quantity can we connect between the one that we know how to measure and the one that we want to report based on the physics that we understand? And what's nice is that as discoveries are made, basically new physics gets incorporated and we can devise new quantities to report, even if we are using the same quantities that we're measuring. But of course, this new discoveries can also lead to the measurement of new quantities. And with this, I'd like to stop and just acknowledge, many students and postdocs that I had the pleasure of working with that have contributed to this work over the years, and take questions.
With the SCT, do you have to destroy sample in order to, get the fractionalized measurement?
So the question is whether the SCT is invasive in any way. Do you need to destroy the sample in order to be able to see the fractionalization of charge? So no, one of the nice thing about this SCT, the single electron transistor, is that it's this technique here. It's that it is very non-invasive. It completely, the sample doesn't know that the probe is there, almost entirely.
How do you move that tip so precisely over the surface of the material? What's the machinery behind that?
Right. So the question is, how do you move the tip over the material? So what we're using are what's called piezoelectric motors. These are materials that when you apply voltages to them, they deform. And the deformation is very, very precise. The translation between voltage to displacement need large voltage to get small displacement. So it's very, very precise. Bigger challenge actually is not moving it across, is not crashing. And there are various techniques that are being used. And Ali, of course, is also one of the experts in scanning probe techniques. There are various techniques that are used in order to maintain constant height above the surface and make sure that you're not crashing.
All right. Are any of these measurement techniques, in your estimation, sensitive enough to measure the subtleties of a single covalent bond, like an organic piece of matter or something like that?
So the question is, do we have enough sensitivity to observe a covalent bond? So the way the technique is now, the way I described it, the spatial resolution is about 100 nanometers, whereas the size of a covalent bond is maybe an angstrom or a few angstroms. So what would happen is that if you try to see that with these tips, you're going to be averaging over many, many of these covalent bonds. So you need something that has a much higher spatial resolution. In fact, there is beautiful work that's being done now at Weizmann Institute in Israel that is developing these kind of potential probes, the same basic physics, but they have nearly atomic spatial resolution, unlike this one that has 100 nanometers, which is kind of like 1,000 atoms. So I think in the future, this will become possible. Of course, the challenge is that it's not only enough you have potential of this kind of tiny spatial resolution, you also need to be able to bring your probe with similar distance from what you're trying to image. So this would mean that if you're trying to image a covalent bond of molecule, you're going to bring your probe to within a few angstroms of that molecule. That's potentially doable.
Well, originally you said that electron was elementary, they can't break it down. But then you have the 3 1/3 charges and those look like particles. How does
Yes.
that work?
Right. So the question is how to reconcile the fact that electrons are fundamental particles and you can't break them apart, yet we're seeing fractionalized electrons. So the answer is that an electron is a fundamental particle outside of matter. In vacuum, if you take an electron, it's going to have one charge E and a spin a half. Now you take 1 billion of those electrons and you cram them inside a material. They're all interacting. Somehow nature conspires to give you the way they interact is to produce something that behaves as 1/3 electrons. It's each one of these particles that I was imaging, this 1/3 part charge, is in fact composed of many, many electrons inside the material. All of them are working together to behave as if you have 1/3 charges.
So what's the spin relationship? Does the spin fractionalize at all?
Yes, the spin can fractionalize. The question was, can the spin fractionalize? And yes, the spin can fractionalize as well. In fact, there are other, I didn't show this, but you have particles in which you have spin moving without charge. So you can have an electron in which, or a particle in which you strip spin from the charge. It's like having a marble that has a color. You can move the marble without the color, and you can move the color without the marble. So it's very, this is the fun thing about these quantum materials, is that they have these very peculiar things that are only existing inside the material.
The macroscopic capacitors are nonlinear. You've treated yours as linear. To what extent does the nonlinearity of capacitors come in?
So in these experiments, so the question is, capacitors are nonlinear, and especially when they're large and when you charge them to very large number of electrons, does the nonlinearity of capacitance play an important role? It doesn't really, because in effect, we're calibrating. So what we're doing is we're constantly calibrating our sensor. So we're basically, we're exciting, we're producing a known change of voltage and seeing our response, and then we're doing our measurement, comparing the two. So we don't really care whether the relationship is linear or slightly nonlinear, because we're constantly calibrating it out in practice.
You have the 1/3 electron. Can you have like 1/5 or 1/10 or 1/12?
The answer is yes. So it's much easier to get 1 over odd integers, 1/3, 1/5, 1/7. Under more complex conditions, you can have even denominator, like a quarter. And that actually has to do with pairing of these bizarre particles. So not only you have bizarre particles, now they form pairs, and that can give you quarter charges. Yes, you can have whole zoo of different charges, but they emerge under different conditions, so they're not all living together.
Yeah, what temperatures is operating?
So most of these measurements are done around 0.5 degree Kelvin. The question is on what temperatures. So these measurements are all done around 0.5 degree, and the measurements that I've shown here today were all done at room temperature, actually. But there's a lot of interesting physics also taking these probes down to cold temperatures, where materials are producing some interesting physics. But yes, both room temperature and low temperature.
Well, mine was just related to that. There's the super cold temperature. Is that because that's the only way you'll see the properties you're looking for, or is it because that's the only temperature the instrument will operate at?
The question is whether the low temperature is because that's the only temperature the instrument will operate at, or is because the physics only exists at low temperatures? And the answer is yes to both. So experiments that, so this instrument here operate at a whole range of temperatures, all the way from very cold to very hot. And so if we have a material that has a physics that emerges only at low temperature, we'll cool the device down. This technique only operates roughly below 1 degree Kelvin. So you have to cool it down, but the physics of fractionalization, for example, also only exists at these very low temperatures. So get them both simultaneously.
Okay. There's some instances in medical imaging where a millimeter resolution is not good enough. Of these technologies, can you know, extrapolate how we could get finer resolution on tissue?
So I think there are even startup companies that are working on this problem. In fact, perhaps the biggest challenge and the one that would be most rewarding using these techniques is to use them to really image structure of molecules. Look at the nuclear spins. I was talking about the electron spins. Looking at the nuclear spins is far more challenging because the magnetic moment of the nuclear spin is 1,000 times smaller than that of the electron. But yet they can really allow you to see the structure of molecules, something that's very, very hard today to do. And if you could do that, then it would tremendously aid in drug design, etc. So this is a direction that there are quite a few groups working on, and it's going to be a very impactful one if successful.
Okay, with that, let's thank Amir.